Hi folks, the following video is going to discuss frontier molecular orbital theory. This is an application of molecular orbital theory to organic reactions. To apply what you learn about molecular orbitals to organic chemistry reactions, we need the concept of what's known as frontier molecular orbital theory. Sometimes frontier molecular orbitals are known as FMOs. The concept of this theory, which was actually awarded a Nobel Prize in chemistry, the idea is that it's only the frontier molecular orbitals, molecules HOMOs, LUMOs, or SOMOs, that matter in our chemical reactions. Ignoring SOMOs and radicals for now, I want to think about some of our common motifs of organic chemistry. The pi bond, the sigma bond, a lone pair, or a cation or incomplete octet. We'll want to think about what are the HOMOs and LUMOs for each of these classes. The HOMO of a pi bond has our side-on overlap of p orbitals, with shading matching, and our LUMO for the pi bond, known as the pi star antibonding molecular orbital, has lobes splayed away from each other and a node down the middle of the molecule. In terms of sigma bonds, we made these of either s orbitals or hybrid orbitals. Most commonly, we're going to see the hybrid orbital variant for our organic reactions, so I've drawn that here. Our HOMO for the sigma bond, known as the sigma bonding molecular orbital, has the large lobes pointing in. In contrast, our LUMO, or sigma star antibonding orbital, has the large lobes pointing out instead of in, and you have a shading mismatch in the middle of the molecule with a node through the middle. We haven't talked about lone pairs in terms of molecular orbital theory yet, because unless they're involved in resonance, they exist on a single atom, and they're not really a bond. For a molecule with a lone pair, we'll consider the HOMO to be the hybrid orbital containing the lone pair of electrons. Here, the atom X could be a carbon, nitrogen, oxygen, so on. And we'll consider this molecule not to have a reactive LUMO. In contrast, a molecule where you have an incomplete octet or a carbocation, for these molecules, the HOMO will not be in play, but they'll react at the LUMO, which will be an empty p orbital. In the example pi bonds and sigma bonds shown above, I'm assuming a nonpolar bond, like between two carbons. But if you have two atoms participating in the bond that have different electronegativities, the HOMO will always have the larger lobes on your more electronegative atom, while the LUMO will have larger lobes on the less electronegative atom. In terms of applying frontier molecular orbital theory to organic chemistry reactions, and not just molecules, we're going to assume the following. Our curved arrow mechanisms, or electron pushing, is going to represent an interaction of a filled orbital with an empty orbital. The filled orbital we're going to think about is the HOMO of the nucleophile, and the empty orbital we're looking at is the LUMO of the electrophile. As an example, let's consider an SN2 reaction. We're going to imagine an iodide anion reacting with a chloromethane molecule. My curved arrow mechanism is going to have two arrows. The iodide is using a lone pair to form a new bond to carbon at the same time that the carbon-chlorine bond is breaking, and the electrons are going to chlorine. This forms iodomethane and the chloride anion. In this reaction, the iodide is serving as the nucleophile, and the carbon is acting as the electrophile. In terms of our frontier molecular orbitals, I want to think about the HOMO of the nucleophile and the LUMO of the electrophile. The HOMO of my iodide nucleophile is going to be a lone pair in a hybrid orbital. And in terms of my electrophile, I'm going to look in particular at the carbon-chlorine bond that's breaking. The LUMO in this case is the sigma star antibonding molecular orbital. I've drawn the lobes on carbon as larger because it is less electronegative than chlorine. So this is where what I think is the coolest thing about frontier molecular orbital theory comes in. Imagine you didn't know anything about the SN2 reaction, and you wanted to pick where the iodide nucleophile is going to attack. What you want to do is locate the largest lobe of your LUMO. This would be the lobe on the backside of the carbon, and this is where your nucleophile is going to attack. If I wanted to describe this frontier molecular orbital interaction, I would say that it is donation of an iodide lone pair into the sigma star antibonding orbital of the carbon-chlorine bond. As I mentioned before, the nucleophilic attack is going to occur at the largest lobe of the LUMO. This is on the back side of carbon, across from the chlorine. And the coolest thing is just thinking about the largest lobe of your LUMO, you would correctly predict the fact that SN2 reactions have stereochemical inversion, or the nucleophile always attacks opposite the leaving group. In summary, I've outlined some of the frontier molecular orbitals to pay attention to. These are the HOMO and LUMO of sigma bonds, pi bonds, lone pairs, and empty p orbitals. And I've talked about one example of applying frontier molecular orbital theory to an organic reaction, the SN2 reaction. In class, we'll practice more of identifying frontier molecular orbitals, as well as using this theory to describe other types of organic reactions. That's it for this video. I'll see you in class.